Assalamu alaikum, my dear students. Hope you will be fine and okay. I welcome you all into my today lecture. Today is our lecture number 23rd, uh, unit number 13, and we are now starting the new unit, electromagnetic induction. Our today topic will include induced EMF, the types of the induced EMF, static, dynamic, and then Faraday law, and then the Lenz law. So let us start with the name of Allah Almighty. The electromagnetic induction. What is the electromagnetic induction? Electromagnetic induction is, in fact, it is the process of it is the process of generating it is the process of generating induced current, induced EMF, or you can say current, because current is always caused by the EMF. Induced EMF or current due to the relative motion due to the relative motion between a magnet and a coil This phenomena or this process is called the electromagnetic induction. The phenomena of electromagnetic induction was first discovered by Faraday, and that was it was 18 this was that is the in 1831 by Michael Faraday. By the Michael Faraday. Now, this was a pre-planned experiment, and he was intent, and he already knew that this is going to happen. Reason why? When in 1826, when Oersted discovered the magnetic effect of the current, if you remember, when there is a current in a conductor, then there is magnetic field around the current carrying conductor. There is magnetic field around the current carrying conductor. Oersted discovered this effect accidentally. It was all accidental. It was what? It was all accidental in 1826, as I explained to you in my early lecture in the previous unit, that he was going to show that there is no connection between electricity and magnetism, but the nature proved a different thing, and it came out that there is associated magnetic field around the current carrying conductor. So class, you know that physics allows symmetry. If one thing is true, then indeed the opposite is also true, right? If a moving charges constitutes a magnetic field around them, then can a moving magnetic field may constitute current in the nearby region of a conductor. This is what Michael Faraday, who was one of the genius scientists, thought, right? And he performed in an experiment, and since, as I told you, physics loves symmetry, it came out to be true that yes, a moving magnet may produce induce current in the nearby coil. His entire work was pure, that was experimental, but it did not include even a single equation. Later on, it was the Michael, it was the Maxwell. He was also one of the genius scientists. Later on, it was the Maxwell who gives a mathematical form to the uh, Faraday work in the case of electromagnetic induction. So it is electromagnetic induction is in fact the process of generating induced EMF or current due to the relative motion between a magnet and a coil. What I means by the relative motion? By the relative motion, I mean that whether if the magnet moves or the conductor moves or if both move, right, then there will be what? There will be the induced current in the coil. Now there are few important aspects here. First, the which I want to tell you is the number A, the cause of this induced current. Number B, I just want to know about the magnitude of this induced current, right? That what will be the magnitude of this current and what will be the direction of this induced current. So all the question I will answer one by one. Clear? So let us we start. You see here that there is what? That there is a magnet, as you see, look. The magnetic field lines direction is indicated here as you see in the diagram. This is the direction of the magnetic field, which is indicated by the arrows here and here as you see. Look, so now you know that the magnet is also at rest. Yeah, there is another question also which I want, later on I'll forget. That if, yes, if there is induced current, then it is energy. The D question is where does it comes from? Where does it comes from? Where does it come from? This is also what I want to answer because these are important. Class, you see that there is magnetic induction. That magnetic induction is indicated by B. You see there is a coil or a loop is, let me label it for you. This is a single loop or coil. Okay, and here you see a bar magnet. Now, when I just break the path of the loop, right, and if I just connect the galvanometer in the circuit here, look, here is the galvanometer, right? I connected the galvanometer right in the beginning. When the magnet is stationary, the coil is stationary, then the galvanometer needle indicated 0, showing that there is no current. Now, what the Faraday did, the Faraday the move the magnet with a velocity v towards what? Towards the coil. And a strange thing happens. The galvanometer needle now indicates the presence of the current, that current we call the induced current. We call it what? The induced current. Induced current. The galvanometer indicate a current called the induced current. We don't know in which direction. We will discuss it then here at its appropriate place. Right now, our interest is in the induced EMF. So let I say that it will indicate some current. When you bring this nearer, let's say for example, when you move the coil in the direction is indicated by this. So what you see here, that you see that there is what? That there is the induced EMF or current in the coil. Definitely, because induced EMF will be the result of some induced voltage or some induced EMF or what? Or sub induced EMF. Now where does this comes from? Now before you have seen the magnetic field already exists before also. But since there was no motion, motion is also not the, in fact, the causes. Rather, it is something else. It is the moving magnetic field which produces induced EMF. Moving magnetic field, which is the cause of what? Which is the cause of this induced EMF. So the moving magnetic field does this. So that moving magnetic field I would label as the changing magnetic field. So whenever, what is the result? That whenever there is what? Whenever there is the changing magnetic field in the nearby region of a coil, then what happens? There will be induced EMF. What is this? This is changing flux. What? The rather, I would say that this cause change of flux. So what I can write here now, that the exposure of the conductor to the changing magnetic field result electromagnetic induction. What I can write? That the exposure of what? The exposure of the coil or conductor whatsoever, anyone you can write, to the changing magnetic field. What? To the changing magnetic field results what? Results this electromagnetic induction, right? Look now, in the same way, if you match it to the magnetic effect of the current, whenever the charge moves, there is magnetic field associated with it. In the same way, whenever a conductor moves, there is what? There is the induced EMF associated with it. This is one thing. Now, when you stop the magnet, the induced EMF in the loop disappear and the galvanometer indicates zero again, right? But if you keep it moving, this time now in this direction, as you see, if you move it in this direction, the same process is repeated. But what happens this time? Again, there is induced EMF, but this induced EMF is now in a direction opposite to the previous one. The galvanometer needle will show you deflection in an opposite direction. It means that by reversing the motion of the bar magnet will cause reverse in the direction of the induced current. In the same way here, if you reverse the direction of the current in the if you reverse the direction of the current, then what happens? The direction of the magnetic field also get reverse. Instead of anti-clockwise, it become clockwise. And now look, how is it similar to that? Look at the symmetry. The same thing happens here. Now, look, one thing which I want to clear, whether this changing magnetic flux, whether the change of the magnetic flux is increasing or if it is decreasing, in both way it is change and it will result the induced EMF. Before, when the magnet was moved towards the coil, flux was increasing and there was induced EMF and it was in one direction. But if you move in this direction, the magnetic flux decrease, but still this decrease is a change. And again, there is induced EMF in the coil. Now, look, what if we keep the magnet stationary and if we would like to move the coil towards or away, then what will happen? The same will be repeated, right? If you move the coil towards or away, in both the case, there will be induced current in the coil. The induced EMF will be there, right? So in both the cases, we are actually getting what? We are getting a changing magnetic flux, right? So the changing magnetic flux, actually our magnetic field can cause this thing. So now how we can increase the magnitude? Yes, that if we have a powerful magnet, that is, if you use a strong magnet, that is that another one important thing. Later on, I'll be explaining this thing to you in a Faraday law. Right, the number of turns in the loop can affect your induced EMF. Right, the area of the loop can also affect the induced EMF in number of ways. It can be increase or decrease the rate, that is the speed of the magnet. The faster you move, the faster the flux change and the getter will be the induced EMF. In the same way, if you increase the current here, increasing I, increase what? Increase B. So the same way, increasing this V may increase the induced current, right? One is this thing. The second important point, as far as the proper magnitude and direction is concerned, I will revisit. Where does it comes from, right? This is the question. Whether the law of conservation is violated in this case, and the answer is no, right? Look, when you move the magnet, then the potential energy stored in your body in fact changes to the kinetic energy of this moving magnet, and that kinetic energy of the moving magnet is transferred to the electrons in a conductor with the help of changing magnetic field. So here the changing magnetic field transfer that mechanical energy into what? Into the electrons, and the electrons acquire kinetic energy in one direction and will become the cause of what? The cause of the current. So you see that a mechanical energy or kinetic energy is converted into electrical energy. Later on, I will tell you also, right? And this will be one of from the great law, the known as the Lenz law, that we will validate the law of conservation of energy in this case also, right? So that is all about the that where does it comes from. So it comes from nowhere actually. So it is the kinetic energy which changes into what? Into the mechanical energy. So one is this thing. Second important point, that how we can get this changing magnetic flux. So when I explain to you the Faraday law, that inshallah at that point, this changing magnetic flux, right, ways or methods to get this changing magnetic flux, I will explain it to you. Now, the induced EMF can be produced, one which we call the static magnetic field, the static induced EMF, and the other we call the dynamic induced EMF. That is, in the uh, static induced EMF, that is here the moving magnet. This is caused by what? That is moving magnet or a magnetic field in the nearby region of stationary coil. In the nearby region of a stationary coil. Of what? Of a stationary coil. Clear? And the dynamic induced EMF is moving coil. Moving coil in the field of what? In the field of uniform magnetic field. Uniform magnetic field. So both way you can get it. Okay, so whatever you either move this or that, it will produce induced EMF. But remember, even if you move both moving magnetic field and moving coil together will result when the relative velocity of them is not zero. Yeah, very simple. I would like to tell you, as long as there is changing magnetic flux, so even if you both move in the way that you can get a changing magnetic flux, the answer is yes, there will be induced EMF. Now let us come to the Faraday law. That what is the Faraday law? The Faraday law. As I told you, that he discovered this effect in 1831. Right? According to the Faraday law, this is what I told, that when you move it towards or away, in both the cases there will be induced EMF. Faraday law tells us that the induced EMF, the induced EMF, the is directly proportional, is directly proportional, it is directly proportional to the rate of changing magnetic flux, to the rate of change of magnetic flux. Mathematically, we can write that the induced EMF is directly proportional to the rate of change of magnetic flux, delta X by delta T. That is, if the flux through the coil is, see here, look, if the flux through the coil changes in time, then there will be induced EMF in the coil. And this induced EMF mathematically can be obtained from the expression which you see here. And now I will explain this to you. You see here, the negative sign here indicates the direction or the polarity of the induced EMF, and the number of turns in the coil, as I already told you. Right, where psi is, where, sorry, this is pi, okay, not psi, where pi is the change in pi, that is actually the magnetic flux, which is equal B dot A. And here I will discuss this with you. So if you increase n, this increases. As far as the negative sign is remaining, then I will explain this when I explain to you the Lenz law, right? It indicates the direction of the induced current, and that can be found with the help of the Lenz law or Fleming right hand rule. Okay, so look, as we know that the change of flux B, we can write better to write B A cos theta, right? Then I can write this equation in number of ways. You will notice it right now. Let us see, for example, may I write this delta B, right, into B A cos theta into A cos theta. This is one expression, right? The second expression is that what I can write here is delta B, sorry, let me make it more thin. Okay, see here, look, I may write it like this, B into delta A cos theta. Even I may write it like this, that B A cos delta theta, right? And another way I can write it like what? Like B delta B delta A into cos theta. Could be even more, but I just, there is nothing here, but I want to add another one. Changing current. What? Changing current. Changing what? Changing current delta I. This is not here directly, but I will tell. So you see 1, 2, 3, 4, and this is 5. So what all these mean for us? The first one, this is delta B. This is changing magnetic field. Changing magnetic field. Yeah, that if the magnetic field changes by around, then what happens? The flux get changes. This is what? Changing area. So if you change the area, cross-sectional area of the coil, even if the B is fixed, for example, look at this case here. If your magnet is stationary even here, and if the coil is stationary, but if you just what compress or stretch the coil, either in stretch or if you compress your coil like this, then in the same case again, what happens? There will be what? There will be the induced current, right? Now this is what? If your B is constant, A is constant, but delta theta is changing, means changing the orientation of the coil. Changing what? Changing the orientation of the coil or of the magnet even. Changing the orientation, the position of the coil or the magnet all of a sudden. So with the change of angle, you get a change of flux. And this will results the induced EMF. If you change B, both B, A changing, still there will be changing magnetic flux and there will be induced EMF. Similarly, changing current. This is actually the phenomena of what? This is called the phenomena of mutual induction. Mutual induction. That is, that you know that there is associated what? That there is associated magnetic field around the current carrying conductor. So when your current is changing, definitely the magnetic field will be changing and it will cause a flux, and it may be the cause of induced current in another wire or in another nearby coil. That is what you might have heard, or you are maybe using at your home, are just like a cardless charger. The cardless charger work on this principle, right? So this is also the way in which you can transfer energy from one point to another point. So the next important one is the Lenz law. As I told you that about the magnitude, I told that if you increase all these factor, magnitude can increase. But what could be the direction of the induced EMF produced in the circuit? So the Lenz law is here. The Lenz law does two things for you. One, that indicates what the Lenz law help you find or indicates the direction of what? The direction of the induced current. The direction of the induced current. And the second part, right, that validate the law of conservation of what? Law of conservation of energy. Law of conservation of what? The conservation of energy. These are the two broad jobs of the Lenz law. According to the first part of the Lenz law, this law states that the direction of the induced current, the direction of the induced current, the direction of the induced current is such that it always oppose the cause reducing it. The cause reducing it. It always opposes the cause reducing it. Okay. So you know there are always two things, the cause and the effect. So the direction of the induced current is such that it always opposes the cause reducing it. What does this mean? You have the cause and you have what? And you have the effect. For example, look, what is the cause? Cause is the motion of the magnet, for example, moving or changing magnetic field, moving magnet. Right? And what is the effect? Induced current. So in one way, what does this law says? That the induced current opposes the motion of the magnet. How is it so? Right? Here the answer is pretty yes. Look, that whenever, see here, that whenever you move the magnet, you just see, look, this is a loop or coil, there is a galvanometer. When you move the magnet into the coil, just see, look, the direction of the velocity is indicated up. Then what will happen? That your motion is resisted. If you do it experimentally at your home, then it is quite sure you will feel that if you move the magnet towards the coil, the motion of the magnet is resisted. You will feel that resistance in your hands, right? The reason is why? Because if there is induced current in the coil, which is indicated here, right? Now, you know, this is a current, not alu ka chalu. So you saw this, you see that when there is a current moving in the coil, what will happen? There will be definitely magnetic field associated with the induced current, right? I may call that as the magnetic field of the induced current, right? Yeah, I can say the B induced. What? B induced. Now this B induced orient in such a way that the north is facing the north. What? The north of B is facing the north of the permanent magnetic field. This is quantum magnetic field. Here the magnetic effect is visible, but there is no physical magnet here in this coil. And that bar magnet, which we sometimes call the electromagnet, it has its north facing the north of the permanent. This is why when you bring it nearer, its motion is resisted. This is why you will continuously supply energy to keep the magnet moving if you want to produce more induced EMF. So this is in consistence with the law of conservation of energy. If you want to keep it moving, you have to provide energy, right? Why? Because it is not a self-perpetual process. If that magnet would lie in a way, for example, if here would become south, for example, if this would become south, then what will happen? It would attract the magnet towards itself automatically. And induced EMF would be generated at the cost of no input energy, which is against the law of conservation of what energy. So you have rightly seen that this validates the law of conservation of energy also. Energy does not comes from the sky or for no reason, right? This process is not the energy machine. Remember, this is not a situation like that this generator produce electrical energy for us. Rather, this is a kind of converter which convert electrical energy into, sorry, mechanical energy into electrical energy. And that changing magnetic field transfer does this thing. Clear? Now, when you move the magnet away, what happens? The direction of the induced current gets changed, right? And what happens that here now, definitely you know that whenever there is a north pole, so at the north pole, what happens? At the north pole, if you look from the bottom, the direction of the current appears to be what? Definitely anti-clockwise. So here in the loop, the current, when you see from the bottom, the current will be what? In the anti-clockwise direction. But when you move the magnet away, still you will feel resistive forces in your hand. It will not allow you to take the magnet away. Why? Because this time, before there was increasing magnetic flux, now there is decreasing magnetic flux. And as I told you, that decreasing magnetic flux also produce induced EMF, but in the opposite direction. So what will happen here? The induced current will have the induced magnetic field, and that induced magnet have now the south pole here, right? It has what? The south on this side now, the south pole of the magnetic field through this loop or coil or through this solenoid. And you know that unlike poles attract. Their like poles were repelling, but here the unlike pole attracts, so still its motion is resisted. So in order to produce the induced EMF or to maintain the induced EMF, you have to keep the magnet constantly moving, and this will require energy. And in order to increase the induced EMF, then there will be greater induced magnetic field and then greater induced opposition from the magnetic field, and you need more energy. This is why to produce energy on the industrial scale, you need large, for example, dam to run turbines. Turbines runs generator, and this is how electricity is produced, right? So that is all about the Lenz law. Now the right hand, the Fleming right hand rule, that is very simple, that if you just stretch your three fingers like that, and then this here, the thumb will indicate the direction of the motion of the coil, and the fingers will, the first finger will represent the field, and definitely the second finger will point in the direction of the induced EMF produced. So you can just refer to your book for the diagram for the current direction indication using the Fleming right hand rule. Here I did it with what? With the Fleming left hand rule. Now there are certain application of the Faraday law that is just like a newspaper kind of topic. You can read and learn about that. That is for in the seismic department, right? So you can see it there. Now thank you very much, and inshallah see you in the next lecture.